It's one of the biggest mysteries in genetics. Have you ever wondered why two people, let's say they're siblings, can have the exact same genetic risk for a disease, but one of them gets incredibly sick, while the other is, well, almost completely fine? It's this puzzle that scientists have been chipping away at for decades, and now thanks to a pretty revolutionary new approach, we're finally starting to get some real answers.
This is the question, right? This is what drives so much of modern medical research. It tells us that just knowing you have a so-called disease gene is not the whole story, not even close. There's something else happening, something in the background that's pulling the strings, and figuring out what that something else is, well, that could change everything.
For the longest time, genetics was treated like studying a soloist, focusing on one single gene and what it does. But the reality we now know is so much more complex. Our genome isn't a soloist, it's a symphony. Thousands of genes are all interacting, each playing a tiny part to create the final outcome. The old way of looking at it just can't keep up.
And that brings us to this new field called systems genetics. It's all about understanding how every single instrument in that genetic orchestra works together to create the music of our biology, both when things are going right and when they're going wrong. But of course, that brings up a massive question.
Exactly. If you're trying to figure out a symphony, you can't just listen to the violins and call it a day. You need a way to hear every instrument, to understand how they all harmonize and play off each other. To do that for genetics, you need a completely new kind of tool.
And that tool is GeneNetwork. I want you to think of it as a massive online library that's been combined with a super powerful detectives toolkit. It was built specifically to solve these complicated genetic mysteries, and it does it using 3 core components that work together beautifully.
Okay, so first up, you have the database itself. And this thing it's like a genetic encyclopedia that's been growing for more than a quarter of a century. It's got layers and layers of info on thousands of different mouse strains, their complete DNA, which genes are switched on or off in different tissues, and data on more than 4,500 measurable traits, everything from brain size to blood pressure.
Second, and this is the real secret sauce, is something called the BXD mouse family tree. Researchers started with 2 very different parent mouse strains. We'll just call them B and D. They bred them together over and over again for many generations, basically shuffling their genes like a deck of cards. The result? Over 150 unique new strains, where each one is a slightly different but now genetically stable mix of the original B and D parents. This gives scientists an incredible, reproducible way to study how natural genetic variation works.
And third, there's the analytical toolkit. This is the powerhouse software that sifts through all that mountains of data to find the needles in the genetic haystack. Its key tool is called QTL mapping. Basically, the software looks at all the mice with, say, high blood pressure, and it asks, okay, what specific genetic variations do all of these mice have in common that the low blood pressure mice don't? It's a way to zero in on the exact locations on a chromosome that are controlling that trait.
So theory is one thing, but how does this all come together in a real-world investigation? Let's actually walk through a case study to see how researchers use this toolkit to solve a genuine medical puzzle.
All right, so a team wanted to figure out why a specific genetic heart condition causes terrible scarring or fibrosis in some but not others. So first, they gave the disease-causing gene to all those different BXD mouse strains, and then measured how much heart scarring each one developed. Next, using that QTL mapping tool, they compared the genetics of the mice that got really bad scarring to the ones that didn't. Bam! That pointed them to specific regions on the chromosomes. And finally, they dug deeper into those regions, looking for which genes were actually turned on in heart tissue. And that's how they could pinpoint the specific modifier genes that were controlling how bad the disease got.
And this brilliant process isn't just for heart disease. Not at all. The real power of GeneNetwork is just how versatile it is. The same basic toolkit has been used to unlock mysteries across a huge range of biological questions, leading to some really amazing discoveries.
In neuroscience, for instance, it's helped identify key genes that control how specific parts of our brain develop. Or in eye research, it's been used to map out the genetic networks that either protect our optic nerve or, unfortunately, make it more vulnerable to the kind of damage that causes blindness and glaucoma. This is the kind of fundamental knowledge we absolutely need to develop new treatments.
And the list just keeps going. Researchers have used it to figure out which of our own genes help or hinder infections like tuberculosis. Others have uncovered the genetic links that tie together things like anxiety and alcohol dependence. It's really a tool for almost any biological question you can possibly imagine.
Now, you might be asking a really fair question here. This is all great, but it's all in mice. Why aren't we just studying humans? And that is a crucial point, and there are a couple of really important reasons.
The biggest reason is this number right here. About 95% of mouse genes have a direct counterpart in humans. We share the vast majority of our fundamental biology. So what researchers learn in these incredibly controlled mouse experiments is hugely relevant to human health, but they can do it in a system where they can control both the genetics and the environment in ways that are just completely impossible with people.
So, when you put this all together, what does it mean for the future? Well, this work isn't just about collecting a bunch of data, it's about building an entirely new way to see and to understand our own biology.
One of the researchers behind this project put it perfectly. He said to think of it as building a Google Maps for our genes. It's a tool that helps scientists navigate the unbelievably complex landscape, finding the routes from our DNA all the way to the real-world traits and diseases we see.
And you know, what's so critical is that just like Google Maps, this tool is free and open to everyone. A student at a small university has the exact same access to all this data and all these tools as a top professor at Harvard. This whole philosophy just democratizes science. It speeds up discovery by letting the entire global scientific community have a shot at finding the next breakthrough.
So the ultimate goal, the end game for all of this foundational research is to pave the way for the future of healthcare. Precision medicine, a future where treatments aren't one-size-fits-all anymore, but are instead tailored specifically to your unique genetic symphony, allowing us to predict risks and design therapies just for you. You know, when you step back, what we're really doing here is building the most detailed map of humanity ever conceived. The work happening at GeneNetwork and in systems genetics is giving us the power to finally read it. And so the real question for all of us is this: as this map gets clearer and clearer, how are we going to choose to navigate it?